Today, we're going to talk about linear models for longitudinal data. So that's kind of a fancy way of saying, what do we do when we have correlated data with a continuous outcome? Well, the way that we deal with that frequently, if we're comfortable with assuming a linear association, is we'll do a linear model that accounts for that correlation. You remember I talked about this a little bit in my lab session yesterday if you were there, but just as a quick summary for other people, one of the big assumptions in all of the regression methods that you've learned so far, linear regression, logistic regression, is independence of observations or of outcomes. So whether I get the disease or the outcome has nothing to do with whether the next person gets the outcome, and their outcome has nothing to do with whether the next person down the line gets the outcome, and so on and so forth. So in correlated data and in longitudinal studies, we have a situation that violates that assumption, that underlies all of the stuff that we do with linear regression and logistic regression. So we have to do something different. And those different techniques are what this course is all about. That's the core problem that we're trying to solve. So we're going to start today by talking about some techniques to account for that correlation and account for the violation of that assumption if you have a continuous outcome, okay? So that's the whole idea of this lecture. And there are three basic things that we're going to talk about, or three basic techniques. There's marginal linear models, random effects linear models, and conditional or transitional linear models. As Dr. K mentioned last week, conditional, transitional is a little bit more complex, has a lot of uncertainty around it, so we're not going to spend a lot of time with that at all. All right. And I am working off Dr. K's slides here, so forgive me if I have to pause for a moment. They're not my own slides, so I may just need a moment to find my place and make sure I'm saying the right things. Okay, so let's start by talking about the three types of models that I just mentioned. Let's start with marginal models. So the slide says that model is the marginal mean, E, the expected value of Yij as a function of important covariance. So it looks just like a normal linear regression model, right? I mean, except for the subscripts down here, the ij's, indicating the ith subject or cluster and the jth observation within that cluster. Otherwise, this model here looks just like the linear regression models you learned about in second semester biostats, right? Hopefully that should look pretty familiar. So how do you know that this is a marginal model? Well, you know that this is a marginal model by virtue of what's not there. There's no random effect, okay? There's no Latin letters, like lowercase b's, and there's nothing else fancy. There's no conditional term, nothing like that, so you know it's a marginal model because it just has your fixed effect predictors, okay, your intercept, and an error term. And by the way, what's the difference between these two models? Does anybody see on the right side of the equal sign? What's here that's not up here? It's an error term. And why isn't the error term up here when we write the model this way? Okay, so when you take the expected value of something, right, this is just good to review just in case you guys don't remember this, but if you have some random variables, okay, let's say you have three random variables, x, y, and z. So the expected value of x plus y plus z is just the expected value of x plus the expected value of y plus the expected value of z. Okay? So when we take the expected value of Yij, we take the expected value of beta 0, beta 1, xij, blah, 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 but the expected value of Eij is what? If we assume, as we normally do in a linear model, that Eij is distributed normal with mean of 0 and mu of sigma squared. What's the expected value of Eij? 0, right? So it drops out when we take the expected value. That's why Eij is down here, but not up here. The different model notations I know when I was taking this course really got me, so forgive me if that was just me and I'm spending a lot of time on something that's not important to you guys, but I'm just teaching from what I know and what I had trouble with to clarify some of the notation issues. All right. So the second model here is an example of a random effects model. And here we're adding in a random effect denoted by a Latin letter, lowercase b, 0i. So in this case, it's a random intercept because it's not multiplied by any x. It's just a random intercept. One thing I wanted to point out is notice how the expected value here is written. It's the expected value of yij conditional on b0i. Can anybody tell me why you have to write it as conditional on b0i if you're writing the expected value? Expected value notation for the model? Here's a hint. What's the expected value of our random intercept according to what's written up here? It's 0, okay? Because we're saying that b0i and eij are both distributed normally with mean of 0. So if we took the expected value of b0i, that would end up dropping out of the model that we wrote up here, which would be no good. We don't want that to happen. So instead of saying the expected value of yij, we say the expected value of yij conditional on b0i so that we can write the model this way. That, just in case you had a question about that, that's essentially why it is. All right, so that's a random effect, and we've already talked some in lecture about what a random effect is. And then we go down here to our conditional or transitional models. Here we're adding another fancy effect, and it's another predictor you see here, but it's actually a previous value of the outcome. So instead of another x, it's actually y sub I j minus 1. Okay, this type of model is tricky for a number of reasons. It's hard to decide when to do it. It's hard to know exactly how to execute it, so I'm not going to spend a ton of time on it right now. Okay? Just know that it's an option, and we'll talk about it a little bit later in the course. All right. So, these are, I want to make sure I covered everything. These are 3 options for how you might want to deal with correlated data when you have a continuous outcome. You could do a marginal model, a random effects model, conditional or transitional model, assuming you're okay with a linear model in general. So here's an example of a problem where this might be applicable. And I think we've talked about this FEV example before, right? Okay, well, just as a quick reminder, we have big K equals 40. We have 40 clusters. Okay, they're kids, as I recall, with n sub I of 5 observations per subject or per cluster. And we have 2 questions that we could talk about with this study. There's the blue question and there's the red question. So the blue question is really just asking you to compare 5 averages. FEV1 at baseline, at a pollution alert, and at 1, 2, and 3 weeks post-alert. And one question that you could ask is simply, are they equal or different? Is the mean FEV in week 1 equal to week 2, equal to week 3, equal to week 4, equal to week 5? There are different ways that you could structure this question, but for now, let's assume that that's what the blue question is asking. It's just, are all the mean FEVs equal in the different weeks? So you've got 5 means across 5 groups that you want to compare. You want to compare the mean in week 1 to week 2 to week 3 to week 4 to week 5. What kind of analytical method that you're already familiar with does that sound like? It sounds like an ANOVA. It sounds like a one-way ANOVA specifically, right? Comparing means across more than 2 groups. 2 groups would be a t-test. More than 2 groups would be an ANOVA. But what's the problem with ANOVA for this study here? That's right, it assumes independence, just like linear regression, just like logistic regression. It assumes independence of your observations, and we clearly do not have independence of our observations here. So, you have to choose some way to account for the correlation. And there are different correlation structures that you could choose. We've already talked a little bit about correlation structures, and we'll talk more about this a little bit later on today. But independence would not be appropriate. You could choose AR1, autoregressive 1, which tends to be favored for longitudinal studies where measurements that are closer in time tend to be more correlated than measures that are further apart in time. as you're dealing with a pretty short time frame here, you could also justify maybe choosing an exchangeable correlation structure, because you're only dealing with a matter of weeks instead of, say, years. So is there really going to be a big difference in how all of these observations are correlated? Maybe, maybe not. That's up to you. Recurring theme of this course, if you haven't noticed right now, is you have a lot of choices that you can make in how you conduct this analysis, and this is just another one of those. And then how would you actually do the analysis? Well, we have three options if we're sticking in the linear model framework: marginal, random effects, conditional, or transitional. Marginal model would work fine, though you could do random effects depending on the research question that you wanted to ask. So for the blue question, a marginal model would probably be fine. For the red question, where you're trying to identify particularly susceptible kids or groups of kids, you're going to want random effects in order to tease out that natural heterogeneity in the population, okay? So what model you're going to do depends a little bit. You could end up using proc mixed or GenMod or Glimmix in SAS to do this analysis. It's up to you. I believe all three of these could handle this study depending on the exact question and model that you wanted to run. So that's another choice that you have to make sometimes. Which SAS procedure? I already mentioned for the red question, we want to find sensitive subgroups. So here we don't want to compare population means. Okay, so it's not an ANOVA exactly. You want to say something about the subjects one at a time, rather than just comparing population means across the weeks. So that would require random effects, as I already mentioned, because then you would have a separate term for everyone to define the response by each of these kids individually. And we'll talk a little bit more about that in just a minute later in the presentation. Here's another example that I believe we've already talked about, a study of the posture of computer operators. Have we talked about this one or just the FEV one? I forget. We've talked about this one too. Okay. 19 clusters, 19 subjects, 6 measurements per subject in the morning and in the evening, Monday, Wednesday, Friday. Clearly correlated data. Before this course, if you were dealing with variation across day and time, this would simply be a two-way ANOVA with indicator variables. But again, we have to assume independence, and we clearly have repeated measures here. So again, an ANOVA would not be appropriate, so we're going to talk about which of these linear models might be appropriate. In addition to day and time, you might want to consider the effect of subject. Well, that would require adding in a random effect, again, to sort of tease out that natural heterogeneity in the population. So here's the data from that study. So as we're trying to figure out, do we have an effective day or an effective time, we can start sort of looking across the sample means here. And we definitely seem to see that Friday has lower shoulder flexion measurements, which are better than Monday or Wednesday. So people seem to maybe have better posture here on Friday, but we haven't done any sort of statistical test to mark out that comparison. Is there interaction between day and time? Well, you could look and say that the difference between the morning and the evening is less on Monday than it is, say, on Friday. So maybe there is some interaction. But again, we haven't done any kind of statistical test yet. But regardless, you'll need to do some sort of analysis that accounts for the correlation, not just typical linear regression and not just a typical ANOVA. So here's some more about that shoulder flexion example. We talked about day and time being fixed factors. You could argue that day and time might be better considered as random factors. Do you remember the key question that you're supposed to ask yourself when determining whether something is a fixed or a random factor? Does anyone remember that? It's if you repeat the study, would you want to have the same levels of that factor in the replication as you had in the original experiment? So let's apply that question to day. Here we have measurements of these computer operators on Monday, Wednesday, and Friday. If we did the study again, would we want to have measurements on Monday, Wednesday, and Friday again? Or could we have maybe different days, Monday, Tuesday, and Friday, Monday, Wednesday, and Thursday. Well, I don't know. That kind of depends on how you philosophically conceive of that. Like if you wanted to cover the whole week, Monday, Wednesday, Friday seems to make sense. Maybe the managers would only let you in on Mondays, Wednesdays, and Fridays, so maybe it does make sense to think of Monday, Wednesday, and Friday as fixed. But maybe you just happen to choose Monday, Wednesday, and Friday out of a hat for some reason. Well, then maybe you would think of day as a random factor. It's not always really clear, and you can make a case for either side, so here's another choice that you have to make sometimes in your analyses. And as long as you can defend those choices, you're in pretty good shape, I think. Let's see. Similar issue for whether time could be considered fixed or random. And yeah, those are the only statements that I wanted to make here, except to say that subjects are probably pretty clearly a random effect. You wouldn't necessarily, if you replicated the study, you wouldn't want to do it on the same people over and over again. You'd want a different sample to see if you could replicate those results. So I would definitely consider subjects random. All right, so this is adding just a little twist to that shoulder flexion example where now we're looking at gaze angle data, and we've added in this other factor of two different raters who are measuring the gaze angle, right? You see this in studies all the time, different raters. So here, we still have K, big K equals 19 clusters, but N sub I is now 12 instead of 6 observations per subject, because we have Monday, Wednesday, Friday, AM and PM, rater 1 and rater 2. 3 times 2 times 2 is 12 per subject. You still have correlated data here, so a naive model would be no good. Now, speaking about fixed and random factors again, what does it make sense to treat rater as? Well, you could think of the two raters that you have as a sample from a larger population of raters that you could have chosen. But I believe Dr. K says in the recording that he went back and talked to the PI for this study, and her opinion was there were only 2 raters that they had on the study. They were only ever going to use those 2 raters, so why not treat rater as a fixed effect? Again, defensible choice on either side, and as long as you can defend it and you've thought through that choice, it's okay. If you're anything like me, you really, 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 really love it when there's a right answer to a question. And the more you study epidemiology, I think the more you realize that there are pretty rarely actual right answers, and there's a lot of choices to make. And so I just encourage you to be okay with making those choices as long as you understand the ramifications of the choice that you're making and you can defend that choice. It's okay that there's not an exact right answer. Science is messier than we'd all like it to be. Okay. So this is just back to the FEV study, just a repeat of the slide from before. So let's focus for a moment on the top question, the blue question here. The primary study objective was to determine whether FEV1, a lung capacity measure, was depressed during a pollution alert. Okay. So let's start by considering a marginal model. This is one analytic approach that we could take to this problem. This is not the only one. This is not the one we had to do. This is just one that we could do. Okay, a marginal model here. 1 and 1 star are the same model in 2 different notations. They are the exact same model. Okay? 1 is simply written in scalar form. 1 star is written in matrix form. So if you want a good example of, what really is the difference between scalar form and matrix form? This right here, great reference. These are the same model. Okay? So we know both of these are marginal models because why? Well, in addition to the fact that marginal model is written right up here, we see that there are no random effects and that there are no conditional effects. So we're dealing with a marginal model, right? It's that simple. So let's focus on model 1. Forget 1 star for a minute. Let's just focus on the top part of the slide and model 1. Notice 1 is written in expected value notation, so there's no error term. Also note the lack of subscripts. Again, this is something that really threw me. You could add in IJ subscripts here, and it would be the same model. you can write it either way. So it's kind of your choice. What do you prefer? I tend to like to keep the subscripts because it really keeps me in mind of exactly what observations I'm considering at any given point. So just don't get thrown, why aren't there subscripts here and there were before? That's why. Well, the fact is you could do it either way. All right. So one thing that I want to point out here is note that the referent group is coded as week 5, which is 3 weeks after the pollution alert. So that's our referent group. We could have made the referent group something else. Obviously, this is another choice that you get to make in analyzing your study. I personally think it would have made more sense to make it week 1, and we will actually make it week 1 a little later in the presentation to demonstrate something else. But for now, the referent group is week 5. So this means, all right, so for simplicity's sake, actually, I want you guys to ignore beta 5 sex and beta 6 race. I want you to pretend like those aren't there for now, okay? So, beta 0, the intercept, is just going to be the mean FEV for week 5, right? Mu sub 5, that's what that is, the mean FEV for week 5. Beta 1, then, based on how we've coded this, will be the difference in mean FEV between week 1 and week 5. Beta 2 will be the difference between week 2 and week 5. Beta 3 between week 3 and week 5. Beta 4 between week 4 and week 5. That's what these coefficients are going to represent. Okay? Now, if we're dealing with the blue question, what would the null hypothesis for no effect of the pollution alert be? So the null hypothesis would be that FEV is equal across all weeks. So in terms of regression coefficients, what would that look like? Somebody want to tell me? In terms of model 1 up there. I'm hearing some murmuring that I think revolves around the right answer, which is beta 1 equals beta 2 equals beta 3 equals beta 4 equals 0. So, SAS-wise, if you did this in prop reg, you'd be assuming that the outcomes are independent, which they aren't, so you're going to use something like prop mixed, and you're going to specify a correlation structure. Again, but we're going to get to specifying the correlation structure a little bit later. Just keep in mind that this is something that you would do in prop mixed. I already talked about the lack of subscripts. So, perfect. All right. So let's go on to, let's talk about model 1 star for a minute here, the matrix notation. So, FEV1I, right here, this bold FEV1I, this is a column matrix. You see it's written as a row for ease of putting it on the slide, but you've got this little apostrophe here, and that means transpose. So a row becomes a column. So this is a column matrix of the 5 responses for each subject, FEV1I1, FEV1I2, so on and so forth. XI is a bigger matrix. It's going to be a column of 1s followed by a column of indicator variables for each week. Beta is going to be a column matrix of the coefficients, and EI is going to be a column matrix of the errors. So you have to spend a little bit of time with this. We're going to talk a little bit more about the general matrix notation of a model a little bit later in the presentation, but it's going to take some time to get comfortable with. Just make sure that you understand what exactly each of these matrices represents in terms of values. Right? These are just the predictor values. Okay, these are the dummy variables, and then these are variables for sex and race right here, where the first row would end up being for week 1, the second row for week 2, the third row for week 3, so on and so forth. All right? Now, let's forget about the marginal model for a second, and let's go to look at what the random effects model might look like for this problem, or for this study, okay? So here, Model 2 and Model 3, these are both written in scalar form, not matrix form. Okay? Scalar form, but they include random effects. Model 2 here includes a random intercept, denoted as BI0. It's a single random effect. And that random effect, it's a random intercept, and if you remember, I think this was Harry, Barry, and Gary, the red lines from Mitch's graphic. That just considers the differences in the overall mean for each subject. And again, we're going to talk more about that and what exactly that means in just a few minutes. But it's an intercept. It kind of goes together, BI0, it goes together with beta 0. It just alters what the intercept is for each subject. When you're talking about the regression line that you're fitting, okay? And then Model 3 has a random intercept and a random slope, which is denoted as BI1, and then you have this indicator variable here, ZIJ, which is 0 if j is 1 and 1 if j is 2, 3, 4, or 5. So this is a slope for the difference between week 1 and the average of weeks 2, 3, 4, and 5, which we'll talk about. We'll talk more again in a few minutes about how exactly that we got there. But this will allow us, this BI1 will allow us to tease out the difference in the responses of the subjects, rather than just the differences between their overall means. It's going to let us tease out a difference in their responses, or a difference in difference in terms of their FEVs across weeks. So which of these models helps us answer the red question? And for your reference, the red question was, a secondary objective was the identification of sensitive subgroups of individual children most severely affected by the pollution episode. So, multiple choice. Which of these models helps us answer that red question? Model 2, Model 3, either one, or neither of them? Anybody say Model 2? Model 3? Model 2 and 3? Neither. Don't know. Not following a word you've been saying. Abstentions. I'm giving you a free pass, people here. I want everybody's hands. Abstentions. Oh, liars. Liars. Lies and falsehoods. All right, well, those of you over here who said Model 3 are absolutely right, okay? Model 3, with the random intercept and the random slope, is going to let us tease out that red question, which is really asking about difference in differences, right? It's asking about which kids may be more sensitive than others to the FEV. To the pollution alerts effect on FEV. All right, now we're going to talk a little bit more about these random effects and how exactly we got them and what they mean. So here's Model 2 from the previous slide, rewritten without sex and race. Okay, so we just dropped beta 5 and beta 6, those terms, just for simplicity here. Okay? But we've got only a random intercept, so it's Model 2. Now, how do we, or really how does SAS, go about estimating the random effects for each subject, and what do they mean? Well, here's the equation for the estimate of the random effect for subject I, because you see it is B sub I is 0. So we end up getting an estimate of a random intercept for each subject. So in this FEV study, how many BI zeros are we going to get? How many random intercepts are we going to estimate? 40, that's exactly right. Okay, 40 subjects, we're going to get 40 random intercepts, one per each subject. Now, for those of you who listened to the recording, this will be a cinch, but for those of you who didn't, what does y bar sub I dot mean? What does that dot represent? It represents sort of everything in that subgroup. So y bar sub I dot is the average FEV for subject I. Okay, I dot, that dot is where you would normally see the J, so that dot stands in for every value of J. Okay, so what do you think y bar sub dot dot means? It's the grand mean, that's exactly right, it's the grand mean. All right, good. You got that? So this is a formula for estimating BI0 hat for subject I. Keep in mind, this is a distinction that some of you may not quite grasp yet, but this is not a parameter that we're estimating, it's a variable. It's a random variable, so just keep in mind that that's what we're estimating. And this shows why the random intercept just considers differences in the overall mean for each subject. Because all we're dealing with, we're not looking at means by weeks or anything like that. We're just looking at differences in the overall mean. This is the mean for subject I. This is the grand mean, or the overall mean. So BI0 is proportional, using this coefficient, to the difference between the mean FEV for subject I over the 5 weeks and the overall mean FEV over the 5 weeks. You'll get 40 different estimates. Again, this will not answer that red question. This random intercept doesn't say anything about whether changes over the 5 weeks are different between subjects. So it doesn't say anything about a difference in the differences question. Okay. Let's move on to Model 3. The first thing I want to say about this slide is ignore the empirical Bayes terminology here. Don't get tripped up with that. Don't worry about what it means. Forget about it. All right? Pretend it's not there. Okay. So here's Model 3, the second random effects model without sex and race. But we see here it's got a random intercept, and it's got a random slope, BI1. So what we're going to do here is just walk through how you would go about estimating the random slope term, BI1, for subject I, and what it means. So let's start by looking at the expected values of FEV1 for subject I in each week, conditional on the random effects. Okay, remember we had to write conditional on the random effects if we're doing the expected value notation so that the random effects don't drop out of the model. All right? So these follow pretty directly from the model and from FE 740, right? Like the expected value of FEV1 I1, so in week 1, is going to be beta 0, the intercept, plus beta 1, because T1 is going to be 1 in week 1, because our referent group was week 5, remember that, plus the random intercept for subject I. Okay, for week 2, we swap out beta 1 with beta 2 because T1 becomes 0 in week 2, but T2 goes from 0 to 1. So now we've got beta 2 rather than beta 1, and we've got the random intercept, and now we've got this random slope here, because remember how Zij was defined. It's 0 if j is 1, so if it's week 1, and then it's 1 otherwise. So in week 1, we didn't have this BI1 because Zij was 0. But in weeks 2, 3, 4, and 5, we are going to have this random slope here, BI1, because Zij is going to be 1 for weeks 2, 3, 4, and 5. Okay? All right. Let's see. Yep, just plugging in 1s and 0s. And now let's look at the box here. Okay. So after a whole bunch of algebra using this system of equations that is in the appendix to this presentation, if you want to go look at it, I will not subject you to that. But if you're one of those people who needs to prove to yourself that this works out, like I am, you can go to the appendix and walk through all of the algebra. And, you know, it's fairly simple algebra. It's just really involved. So I'm not going to, spend your time on it here in class. But if you just trust me, after a whole bunch of algebra that's laid out in the appendix, we get this equation for BI1. And it turns out to be really intuitive. This looks like a mess, but let me translate for you what this equation in the box here means. Okay? The first term. Let's focus on the first term here. What is that? Can anybody tell me what that first term is in plain English? That's right. That's right. It's the overall average for week 1. The difference between the overall average for week 1 and the mean for weeks 2, 3, 4, and 5. So it's taking 2, 3, 4, and 5. It's collapsing it down into one measurement, okay, by averaging it. and it's just saying, okay, overall for everybody, what's the average response from week 1, which was baseline without the pollution alert, to the entire period with the pollution alert and post the pollution alert? Did things get worse from week 1 versus an average of weeks 2, 3, 4, and 5? Okay, this is for everyone. This right here, this looks like a mess. This is the same thing, just for subject I. Okay, so this is the mean change from week 1 across all subjects. This is the mean change from week 1 for subject I. That's it. So it's the difference in the changes from week 1 to future weeks between everybody and subject I. So it's comparing the difference or the slope for subject I to the difference or the slope between week 1 and weeks 2, 3, 4, and 5 for all subjects overall. Okay? So what that means is that when you look at an estimate of BI1, what you're looking at is whether that change from week 1 to weeks 2, 3, 4, and 5 average is, for a given subject, more than the population average for that change, or less than the population average for that change, or pretty much the same. So if you get a positive slope, that person experienced a greater change from week 1 to weeks 2, 3, 4, and 5. Let's see, was there anything else I wanted to say? You'll get, just like you got 40 estimates of B0I, you're going to get 40 estimates of B1I, one for each subject. Importantly, that is specific to the way that this model is written. You don't have to limit yourself to just one random slope, and you don't have to limit yourself to a random slope that looks at the difference between week 1 and weeks 2, 3, 4, and 5 overall. You could have defined as many random slopes as you wanted to, for as many different comparisons as you wanted to. It's just going to make the model more complex and less likely to run. But, you know, you could choose any number that you wanted to and define them however you wanted. So you could define one slope between 1 and 2, one between 1 and 3, one between 2 and 3. You could have all these different random slopes in there. But very, very quickly, because you're having to estimate so many parameters, remember, we're having to estimate 40 values of each random effect. So you're very quickly going to run out of data to make these estimates. So that's why you often don't see, you know, models with a whole bunch of different random effects, because it simply won't run. Okay. So you can scan across the 40 estimates of BI1 that you're going to get to find subjects with bigger than average differences versus those with average differences versus those with smaller than average differences, to ID subjects that are particularly susceptible or not susceptible. That is the red question. Okay? So model 3 is how we answer that red question from the earlier slide, and this is why model 3 will let us do that, because the random slope will give us that answer. All right. Now, I promised you earlier that we were going to change the reference group from week 5 to week 1, just for fun. Yes, Kevin, sorry.
On the previous slide, you're subtracting the expected value of the individual from the population mean, right? So
That's right.
Someone, if a particular subject has a mean that's above the average, wouldn't you end up with a negative slope rather than a positive slope?
Let me think that through. You might be right. I may have misspoken there. If we take a break, I'll try to work that through during the break and make sure I've got it right. But you bring up a good point. One thing that I can say for certain, okay, is that you will be able to scan the values of BI1 for each of your 40 subjects and find ones with a bigger change or a smaller change relative to the average. Whether a bigger change means they are more susceptible or less susceptible, I need to think about that for a few minutes over the break. But you can definitely scan those to find ones with bigger, to find subjects with bigger changes or smaller changes relative to the average. But whether that means they're more or less susceptible is going to be specific to your study and your your specific model. So in this case, I just need to think about which one it would actually be. Okay. Anything else? All right. So we're going to change the reference group from week 5 to week 1. I think that's actually a little more intuitive because it's kind of like, well, yeah, week 1 is our baseline. It's our reference group. So, all right. I hope this will be a little bit more intuitive. This is very similar to the previous slide, right? It's just showing how we get BI1 if the referent group is week 1 instead of week 5. And the take-home message is the equation is the same, okay? BI1 is going to be the same whether the referent group is week 5 or week 1. It's not going to matter. The algebra for this, again, is in the appendix if you want to go digging. But the take-home message is the same formula for BI1 is obtained when the referent group is either week 1 or week 5. The referent group does not matter when thinking about the formula for the random slope. Okay? Now, model 4 and 5. These are the conditional models. This is all I'm going to say about conditional models today. So let's start with model 5. Now, model 4, we're going to start with model 5. The new term down here is beta 7. And it's a coefficient for the predictor FEV1 sub I parentheses j minus 1. So that's the response at time or for observation j minus 1 when we're trying to predict the observation at time j. Okay? So this is something called a lagged outcome variable. Here, because we have just j minus 1, we're only conditioning the current response on the one response at the immediately preceding time point, but there's no rule that says we have to only use the immediately preceding measure to predict. You don't just have to use the measure at j minus 1 to predict the measure at j. You could use j minus 2 or j minus 3. Unless you discover that time is nonlinear, I would not recommend using the observation at time j plus 1 or j plus 2, but it's up to you if you can go ahead and make that prerequisite of the proof that time is not linear, and I'll be really happy with that if you can do that. In fact, I'll convince Dr. K to give you an A in the course. You have my word. All right. So this is just using a lagged response. Model 4 is similar, but it's using something called a lagged residual. Okay? So lag, previous, there's a time gap. It's a lagged residual from the difference between the actual FEV at j minus 1 and that predicted by the model at j minus 1. So, conditional models, you can have a lagged outcome or a lagged residual, and they don't just have to be time j minus 1 and time j. Which one of these should you do? Because model 4 and model 5 will often give you very different answers. And the answer is, I don't know, it's unsettled. And Dr. K will tell you the same thing. But I believe he's noted that the literature seems to favor using lagged residuals, which would be model 4 if you have a continuous outcome. But I'm sure that you could justify using a lagged outcome if you so desired. An even broader question than that, which Dr. K has brought up before, is when do you even use a conditional model? And the sort of tautological answer is if you want to predict an outcome from an earlier outcome, you have to use a conditional model because you have to use that earlier outcome as a term in your model, as a predictor. It's less clear why exactly you'd want to do that philosophically, but you can certainly think of instances where you might want to do something like that, and it's okay, and it would be great if one of you or more of you wanted to take that on as your project, but you just have to think about whether a conditional model would be appropriate and kind of make that decision for yourselves. All right, so we've gone through the FEV example, and we've tried to apply marginal models, random effects models, and conditional models to that. Now let's talk about some general characteristics, okay? We did kind of the specific example. Now let's talk about some general characteristics of these marginal, random effects, and conditional models. So, slide 17. Here's the marginal model written again in scalar form and in matrix form. Notice that you can also write the expected value version of the matrix form of the model. And there, the matrix of error terms just drops out, just like always, with an expected value model. So this model very much looks like a classical multiple linear regression model, which we talked about, but in contrast to classical regression, the responses for subject I cannot be assumed to be mutually independent, so we need to take into account those dependencies or correlations among the Yij's. And we do that by using a variance-covariance matrix, which we'll talk about a little bit more later, and I'll bring in some of the slides that I went over, I think, in my lab session yesterday to try to make this a little more explicit. So we'll do a little bit of incorporation. All right. So continuing talking about marginal linear models, for the marginal model written in the expected value matrix form, we use maximum likelihood methods to estimate the betas, again, just written in matrix form here instead of scalar, and the values that fill up the variance-covariance matrix for the responses, and that matrix is denoted V sub I. We assume that Yi have a multivariate, the different observations within a cluster, within a subject, have a multivariate normal distribution. And let's see what else I wanted to say about this slide. How many of you feel comfortable with what maximum likelihood is? Do you want me to do like a 5 to 6 minute detour into the likelihood function and maximum likelihood estimation, or do you want me to get on with it? Detour? You want a brief detour? I heard detour first. Sorry guys, you gotta be fast. All right, here's a brief detour on likelihood. This is from yesterday. So, let's see here. All right, the likelihood function. The likelihood function, which hopefully you've encountered at least in name at this point, it's a function of a parameter or a set of parameters describing how likely various parameter values are given some observed data X. Okay, so we have a study that produced some data. And we're going to use that data in order to estimate some parameters. In a regression analysis, what are those parameters that we're estimating? In just a typical like linear regression or logistic regression model, what are we trying to estimate? Regression coefficients, that's exactly right. So those would be like beta 0 hat, beta 1 hat, beta 2 hat, okay? So the likelihood function is what lets us essentially estimate those. It's one method that lets us estimate values for those parameters based on the data that we have, okay? And then, by maximizing that likelihood function, we get the best estimates for those parameters, beta 0 hat, beta 1 hat, beta 2 hat, et cetera, et cetera. We get our best estimates for those by simply finding out for which values the likelihood function using our data is maximized. So let me try to make this a little less abstract, and let's think of coin flips. Let's say we did 100 coin flips, and 55 of them came up tails. Anybody see that coin flip at the end of the Green Bay, Arizona game, though? Anybody see that? In the NFL divisional round? That was wild, the coin didn't flip! How do you, it's like your one job as the referee. Well, it's not your one job, they got like 1,001 other jobs. The point is, when it's overtime, your one job is to flip the damn coin. How do you just toss it up in the, I don't even know how you do that. I could do that 1,000 times and never fail to flip a coin, even if I'm trying. I don't understand, but it happened. Okay, but let's assume that you're not, who was the ref? Anybody remember? It wasn't hockey league. That's all I remember. The guy's biceps were not like 80 inches. No, all right, I don't remember who it was. Point being, you're not that guy. You're actually flipping the coin. Flip a coin 100 times. it comes up tails 55 times. And we're trying to estimate, the parameter that we want to use the likelihood function to estimate is the probability that that coin comes up tails. Okay? So, we're going to get a series of estimates, or a series of values for the likelihood function that look something like this. We're going to get, so we're going to say theta equals p equals the probability of tails. So that's the parameter that we're trying to estimate with our likelihood function. Then, L of theta equals L of the probability of tails. So, what's the range for the values of our parameter? What values could our parameter take on? 0 to 1, exactly, because it's a probability, okay? So we're going to get a function that looks something like, well, I'm not going to write the equation, I'm just going to write it sort of as values that it could take. So we'll have L of 0 equals some value. We'll have L of 0.01 equals some value. We'll have L of 0.5 equals some value. We'll have L of 0.55 equals some value. We'll go all the way down to L of 1 equals some value. And remember that we had 55 out of 100 flips were tails. Okay? So the likelihood function's values, let's just say this is A, B, C, D, and E down here. What I can tell you for sure, the likelihood function, once we go through all the math and figure out the likelihood function, and I'm not going to go through how we formulate the likelihood function with you, but I'm going to tell you that A is going to be less than B, is going to be much less than C, is going to be less than D, is going to be greater than E. So what we're going to see, I promise, is that the likelihood function is going to hit its maximum value at 0.55, because that's the value that our data gave us for the probability of tails. Our data told us 55 out of 100 flips came up tails. So our likelihood equation is going to maximize at 0.55. The exact same principle applies to estimating regression coefficients, except it's a heck of a lot more complicated, and that's why we have SAS do it instead of us trying to do it. I could walk you through this coin flip example right now. We could create the likelihood right here in front of you, but when you get into multivariable logistic regression, you want SAS dealing with all of that. But that's essentially how it works. And that's what maximum likelihood estimation is. Let's see, MLE is used to estimate parameters of interest. What are those parameters? Sometimes the likelihood function L, this is just one more statement I want to make about the likelihood function. Sometimes it's really difficult or even impossible to formulate. We call that intractable. If the likelihood is intractable, you can't do maximum likelihood estimation. So there are various other ways that we can sometimes estimate regression coefficients in models. We can use something called the quasi-likelihood, which is used in some nonlinear models. There's the pseudo-likelihood, and there's something that you're going to encounter later in the course called generalized estimating equations, which extends the principle of quasi-likelihood to repeated measures. So we're going to talk about it much more later in the course, but that's all I want to say about it for now. So just in case you were curious about how exactly maximum likelihood estimation is done, again with thanks to Dr. Mitch Klein, step 0 in his parlance would be to formulate the likelihood L. So you need to actually write out the function, and this is often the biggest challenge. Step 1 is you take the natural log because it makes it easier to work with. You'll just have to trust me because I'm not going to sit here and work through all of this with you right now. Step 2, you take the derivative with respect to the parameter you're trying to estimate. This produces something called a score function. This is important to keep in mind because when we talk about generalized estimating equations, you're going to come across something called a score-like function, and you're going to have no idea what the hell this means. Score-like function is so named because it sort of takes the place of the score function but when you're using generalized estimating equations rather than maximum likelihood estimation. And then step 3, if you remember from your intro calculus, which I think most of you have probably had, is to set the derivative equal to 0 and solve for the parameter. So that's a very broad sketch of how maximum likelihood estimation works. Okay. So that's really all this slide is saying, is that we use maximum likelihood estimation to estimate the betas, and we have to estimate the parameters that go into constructing the variance-covariance matrix for our outcomes, VI. So before this course, you would have just used MLE to estimate your beta hats. But here, we now also have to estimate the parameters that go into the variance-covariance matrix in order to account for the correlation in our data. So that's an added complexity, another set of things that you have to estimate. And we still use MLE for that when we're doing linear models. Okay. Note that the number of parameters that you have to estimate for VI will depend on the structure for VI that you choose. So exchangeable is popular because it's simple. You only have to estimate one additional parameter. For AR1, you're going to have to estimate a few more, one for each observation that you have in a cluster, if I'm recalling correctly. If you have a totally unstructured variance-covariance matrix, congratulations, you're going to have to estimate a hell of a lot of parameters. So that's why oftentimes unstructured, it seems like, well, why would we choose a structure? Why not just let it be what the data says? Well, because that means you have to estimate a lot more things, and sometimes you simply don't have the data available to do that. So it's up to you. You can always try a model with an unstructured variance-covariance matrix and just sort of let the data guide you to constructing that, but I think more often than not, your model ain't going to run. But maybe it will. I don't know. For the life of me, I can't figure out why some models run in SAS and some don't. Just keep plugging away until you get one that runs. That's my advice. If you come to my office hours, that's like 25% of your questions answered right there, so don't come bother me. Just keep running. Okay. Come bother me, please, seriously. It's really boring in there. And I don't like talking to, who else is in there? I forget who else is in there during my office hours, but I don't like them. I don't like talking to them. You guys come instead. Just kidding. Yeah. And on that note, goodbye. No, kidding. All right. A linear model with a random effect. So we just talked a lot about marginal models there. I went into a little detour on MLE. Now we're going to get back to random effects models. So here's one random effect, right? It's a random intercept. Here, I want to take a detour all the way to the end of the presentation. Slide 44. Yeah, this looks hideous, right? Get ready to take some notes on it. I'm going to make it much, much, much clearer. Okay? I'm not saying that Dr. K's slide is unclear. I'm saying that it looks like really bad equations, and they're not that bad once you realize what they're saying. So I'm going to walk you through, line by line, what's here on the slide. We're going to get through it together, I promise. All right. I had lots of notes on this one. Okay. So we've talked a little bit last week and in my lab session as well about the relationship between correlation and covariance. And this follows, all of this on this slide follows directly from that. So if I go back here real quick, just because I know where it is in my slides. It's up near the top. Right. We have equations for the variance, the covariance, and the correlation. And correlation is the covariance, so the correlation between x and y is the covariance between x and y divided by square root of the variance of x times the square root of the variance of y. That's going to be an important equation for understanding this slide. So if you want to copy it down, I'm going to leave it up here while I mumble for a few seconds, but it's going to be nice to have as kind of a reference for this slide. Everybody got it? Did everybody get it? I'm just saying, just this line. Just this line. This is what I'm going to wait for you to copy down. All right? That right there. Everybody good? Everybody's good. I can see it in your eyes. Of course, you're full of lies and falsehoods, so what do I know? All right. So, we've got a model here, Yij equals mu, which is just some parameter, some average, some population average, if you want to think about it that way. And then we have two other variables here. We have a sub I, which functions as a random effect, and Eij, which functions as an error term. They're both normally distributed with a mean of 0 and two different variances. So the variance of the random effect Ai is sigma naught squared. And the variance of the error term Eij is sigma squared. Okay? This is a correlated data model, and I'm going to demonstrate that to you. Okay, so think of it this way. Let's think of, and Dr. K uses, I believe, this exact example when he's talking about this in the recording from last year. So, let's say we have 8 different drugs. So instead of 8 subjects with repeated observations, we have clusters of people taking 8 different drugs. 1, 2, 3, 4, 5, 6, 7, and 8. So G equals 8. And let's say that J is 1 to 10 people who get each drug. And let's say, furthermore, that this drug affects blood pressure. Systolic blood pressure, if you want to get all specific. All right. So then our question is there a difference in Y, in the systolic blood pressure, for each drug? This would be, again, like a one-way ANOVA, comparing mean systolic blood pressure across multiple drugs and then dividing into between and within sum of squares and doing all that business. But in ANOVA, you might have considered the drug as a fixed effect, right? And had like 7 different indicator variables for it in a model if you were doing a linear regression model instead of an ANOVA. But here we're going to make drug a random effect. Now, instead of having a fixed parameter for each drug, we have a random variable. And the difference between a fixed parameter and a random variable is that a random variable has a distribution. Okay, it's not just a fixed value. We observe a value of a random variable, but we could have observed something different because there's some kind of probability process creating this random variable that we observe. Okay, so instead of a drug as a fixed parameter, we have drug as random variable, and it's something that varies and has a distribution. That's our A term, okay, A sub I. So, since A sub I has a variance, let's work with our variances in order to figure out our variances and covariances of our observations, our Yij's. So, the variance of an observation, Yij, is the sum of the variances of each individual term in the model. I'm going to walk you through, right now, line 2. But I'm going to do it in a little more detail so that it's really clear where everything's coming from here. Line 2 starts off with variance of Yij. It's kind of hard to see up there, but that's what it is. So, keep in mind that the variance of x plus y plus z is the variance of x plus the variance of y plus the variance of z if are mutually independent. We're told this, I think, on a prior slide, but let's make that assumption for now. All right, all three of these terms, mu, ai, and eij, are independent. We're going to do that. We're going to make that assumption so that we can take this next step. All right, so then we're going to say that the variance of yij is simply equal to the variance of mu plus the variance of ai plus the variance of eij. Okay? Now, mu is a fixed parameter. It has a variance of 0. Why by mu? Variance of ai. Well, we're given the variance of ai right up there. It's sigma 0 squared. Sigma naught squared. And we're also given the variance of eij, sigma squared. Okay? So that's how we get in line 2 that the variance of yij is sigma naught squared plus sigma squared. That's it. All right, are you with me through line 2? Okay. Let's go into line 3. This is looking for the covariance between two different people taking the same drug. Remember, drug is our cluster now. So we're looking at two different observations within the same cluster. So that third line up there, just for clarity's sake, reads covariance of yij and yij prime. So some different value of j. Doesn't matter what that value is. Okay, but we're looking at the covariance between two observations within the same group. Now, that third line is simply the definition of covariance. So you'll just have to trust me that that third line is what it is. And the covariance of yij and yij prime equals the expected value of yij times yij prime minus the expected value of yij times the expected value of yij prime. I'm just going to have to ask you to trust me on that one. Okay. So, in the fourth line, we want to start figuring out what each of these terms is so that we can get the covariance between yij and yij prime. So we're going to start off with the expected value of yij, which it turns out is the same as the expected value of yij prime, and both of them are just mu. Because for any observation, if you take the expected value of that observation, according to this model, it's going to be mu. Because the expected value of ai is 0 and the expected value of eij is 0. Right? You with me? So that's why these two terms are both mu in the covariance formula. All right? Now, the 5th through 7th lines. This is a bunch of hideous-looking algebra, but it's really not that bad. Okay? We need to get, in this covariance formula, we've already got the expected value of yij, and we have the expected value of yij prime. What we do not have yet is the expected value of yij times yij prime. So in order to get that, we're simply going to plug in yij and yij prime into this expected value equation in terms of mu, ai, and eij. Okay, so we're going to take this equation right here, all right? And we're just going to plug it in right down here to get the expected value of this product. And it turns out, once we go through all the math, we get this really long expected value formula, but the expected value of most of these terms is going to be 0. Okay? The expected value of mu squared is mu squared. The expected value of ai times mu is going to be 0 because the expected value of ai is 0, right? eij and mu goes to 0 for very similar reasons. ai mu again goes to 0. Okay, the expected value of ai squared. We'll get back to that one in just a second. The expected value of ai times eij EIJ prime, that's going to be 0, 0, 0, 0. All of these go to 0 when you take the expected value. So all you're left with is mu squared plus sigma 0 squared. And this comes from a formula for the variance, which I'll provide you up here just for your reference so that you can understand why the expected value of AI squared becomes sigma 0 squared. So that formula is the variance of x equals the expected value of x squared minus the expected value of x quantity squared. And once you work that out, you will see, simply using the values that you're given on this page, that the expected value of AI squared, it turns out, is sigma 0 squared. Okay? But I'll leave that for you guys to work out on your own. So I don't think it's too tough. Okay. So, now, in the 8th line down here, we can figure out what the covariance is between two observations in the same cluster, Yij and Yij prime. Using this formula that we laid out up here, now we have all of the values for its constituent parts, and it turns out it's mu squared plus sigma 0 squared minus mu squared. So it's just sigma 0 squared. That's it. That's the covariance. So now we have the variance of Yij, any Yij, and we've got the covariance between any Yij and Yij prime. So these two values right here, sigma 0 squared and sigma 0 squared plus sigma squared, will plug into your variance-covariance matrix for your outcomes, VI. Your VI will consist of just these two values, this on the diagonals, this on the off diagonals for this model. Okay. And the correlation, using the correlation to covariance formula that I gave you earlier, you can simply work out as sigma 0 squared, okay, the covariance, divided by sigma 0 squared plus sigma squared, which is what you get when you work out this whole square root business right here. Okay. So, the covariance, and by extension the correlation, because one is proportional to the other based on the variances, between two independent people taking different drugs won't be 0 in this model with a random effect unless the variance of that random effect, so unless sigma 0 squared itself is 0. And if the variance of the random effect is 0, you can see what will happen to the correlation. It will go to 0, because it will be 0 over some non-zero quantity, which is 0. Okay. So, hopefully that helps you work through this slide and figuring out in this model with a single random effect, okay, just a random intercept, how we get the variance of Yij and the covariance of two observations within the same cluster. Now that we've done all that, we're going to go back to slide 19. Okay. And talk about this random effect model. And we're getting pretty close to finished for the day. So I can either let you guys take like this, 7-8 minute break, something like that, or we can just push on through and I can have you out of here certainly within a half hour, hopefully like 15-20 minutes. You want to push through? I want to push through. All right, let's push through. Okay. linear model with one random effect. Again, it's a random intercept model. I think he wants me to take a break. It's all right. I could just sit here and twiddle my thumbs for like 30 seconds. You guys want to wait? No. This was great. I went to see. Are any of y'all familiar with the comedian John Mulaney? Okay. Oh, did you see him at the Tabernacle? Yeah, that was hilarious. He came, and there was a guy who, at least in our show, it was only like an hour set, and the dude got up like half an hour in and left to use the restroom or get a drink or something like that. And John Mulaney was making fun of him mercilessly. Were you guys at that show? It was terrible, right? And so Mulaney goes, all right, now he's out. When he comes back in, I'm going to say, I forget what the phrase was. It was something like, and then we all had ice cream. Some total non sequitur based on the joke that he was making. And you guys are all going to just lose your shit and go absolutely wild. And the guy comes back like 5 minutes later, and Mulaney stops right in the middle of his set and goes, and we all got ice cream, and the crowd went, yeah! And everybody went crazy. And the guy looked so confused and it was beautiful. And Mulaney was like, aha! You're not in on it. That's what you get if you leave. So that's what Andrew's going to get. No, not that movie, but it was great. I loved it. All right. No, we're not going to. Hi, Andrew. You just missed a great story. But you didn't miss any material, so there's that. All right. I'll take the story. All right. So, this is just the general form of a single random effect model. Has one random effect in addition to the usual error term. It's called a mixed linear model because it involves a mix of both fixed and random effects, which I talked a little bit about in my lab yesterday, and I think that's all I want to say about this slide. Let's go into a little more detail here. So, if we wanted to work out the variance of this model based on our definitions up here, so again, we've said, just like on slide 44, okay, this is why we went to slide 44 and now we're coming back here, so that this slide makes more sense, okay? B0I is distributed normally with mean 0 and variance sigma naught squared. EIJ is distributed normally with mean 0, variance sigma squared. And the B0I and EIJs are mutually independent. So what that's saying is that there's one random effect, and that after accounting for that random effect, there's no more correlation left in the observations, okay? That's effectively what that means. All right. It follows that the variance of any observation will be sigma naught squared plus sigma squared. You remember that from slide 44? Okay? This is the same model. They're both random effects models with one random effect, okay? And the covariance between Yij and Yij prime is sigma naught squared. Again, you remember that from slide 44, right? Okay. So these values plug right in to the variance covariance matrix for subject I. So the variances and covariances between the responses for subject I is denoted as VI, okay, and it's going to be an NI by NI matrix, so the number of observations per cluster times the number of observations per cluster, and it's going to look something like this. The variances on the diagonals, okay, the variances drop right in here, this goes here and here and here on down the diagonal, and the covariances are all going to be the same. So all of the off diagonals are going to be the same. This is particular to our linear model with one random effect where BI0 and EIJ are mutually independent, okay? So this VI that I'm showing to you is just specific to this model. But it turns out that if you define a model in this way with a single random effect and no other correlations, you will get a compound symmetric or exchangeable variance-covariance structure. That's one way, not the only way, but that's one way that you can get that variance-covariance structure. And what's more, still dealing with the exact same model, okay, one random effect. We've got our variance matrix that we've already defined. We can use our correlation to covariance equation that I let you copy down earlier to define our correlation structure directly from VI, because we know what the square root of the variances, of the constituent variances, are going to be for any given term. And so once we just work out that simple algebra, okay, we're going to divide every term by sigma naught squared plus sigma squared. So all the diagonals go to 1, which says what? Okay, that says that the correlation between observation 1 and observation 1 is 1. Well, thank God, if the correlation between two of the same thing is not 1, we are in really deep trouble. The correlation between observation 2 and observation 2 on subject I is 1. The correlation between observation 3 and observation 3 on subject I is 1. All of those correlations are going to be 1. And then the correlation between observation 1 and observation 2 on subject I is going to be rho. Between observation 1 and 3 is going to be rho. Between observation 2 and 1 is going to be rho, all the way down. Okay? Yeah, merrily down the stream, blah, 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 whatever. Anyway, so the point is that this compound symmetric or exchangeable variance covariance matrix translates directly to a compound symmetric or exchangeable correlation matrix, right? Okay. So the take-home message here is that a linear model with a random intercept and no additional correlation among the residuals, which you could also define as an independent R matrix, we're going to talk about that in a second, yields you an exchangeable correlation structure. If you were to add another random effect, or have a random effect that's not an intercept, or had residual correlation even after accounting for the random effects, all bets are off. You will not necessarily get this nice, simple, compound symmetric structure here. Okay. If you thought the data had a different correlation structure, if you thought for some reason a priori that the data, that an exchangeable correlation structure would not fit the data, you would not want to use this model to model your data. You would not want to use one random effect. You would want to choose something else. Okay? So that's up to you to kind of think about where your choices are leading you, and making sure that that makes sense with the kind of data that you have. Okay. The only thing I want to say on this slide, which continues to look at the general form of a linear model with one random effect, is that you can reorder the terms so that you see that you end up with different intercepts for the ith subject, because the intercept simply, instead of being beta 0, becomes, when you add in a random intercept, it becomes beta 0 plus b0i. So you're going to have a different intercept for the ith subject. And b0i is a subject-specific parameter. And yeah, that's all I want to say on that slide. Okay. Now, in this model, we've added in a random slope, b1i xij. So now we've got two random effects. We got a random intercept, b0i. We got a random slope, b1i. Here it's just one random slope, but there's no reason we only have to do one. We could do more than one, but you have to estimate more and more parameters, and sometimes that gets difficult. But the fact that you can do more than one is illustrated down here in this very general form of the random effects linear model written in matrix form. We could also write it in scalar form, but it's a little bit more confusing if we tried to do that, just because there'd be an awful lot of terms and sigmas and uppercase sigma, summation notation, all that kind of stuff. It'd be a little bit tricky. So this is the very general form of the model that Proc Mixed is thinking about when SAS runs it. SAS is trying to fit, if you run Proc Mixed, it is trying to fit everything that you could possibly say into this matrix notation of a model. And it makes sense if you think about the constituents here. So yi is a vector or column matrix of the responses for the ith subject. So when you write the model statement, you write model something equals something else. Okay, well that first something on the left side of the equal sign, those are your responses. Then you've got x as the fixed factors and beta as the fixed effects. So that's the second part of your model statement to the right of the equal sign. Z for the random factors and BIs for the random effects. So you'll specify those in a different statement that you'll learn a little bit more about later, but there is a way to tell SAS in proc mix that you want such and such random effect. And E is simply the matrix of residuals that you're left over with after you fit the model. Okay. When you're running proc mix, you have to specify a correlation structure for the residuals. That's known as an R matrix. And or you can specify random effects, which go into something called the G matrix. And I'm going to talk a little bit more about that, I think, right about now. Okay. So, in this very general form of the random effects linear model, we assume that the errors and the random effect estimates here are distributed multivariate normal. And if you're not familiar with multivariate normal, it's essentially a normal distribution for a matrix vector rather than a single variable. So instead of just having a bell curve, okay, you'd have a kind of like, I think a bivariate normal is like a saddle type thing. I mean, you have to start, thinking in multiple dimensions, and it's kind of weird, but it's going to be more than just two parameters, because you only need a single mean and a single variance to define a standard or a typical normal distribution. But if you're looking at multivariate normal, you need some more parameters to fully describe that, like saddle surface or even more complex surfaces that you'll end up generating from that distribution when you try to draw it out. So R sub I here, it turns out, is a variance-covariance matrix for the error term, right? Because we're saying that EI, the errors, are distributed multivariate normal with mean of 0, and then some variances and covariances together that create an R matrix that we denote R sub I. Okay? G is the same thing for the random effects. But notice that G does not have a subscript of I. It is not subject specific. So both R and G are variance-covariance matrices. R is a matrix of variances and covariances for the error terms, and G is the variances and covariances for the random effects themselves. But that matrix is not subject specific. The overall VI, so the variance-covariance matrix for the responses, that's what we're ultimately interested in, right? That's how we're accounting for the correlation, is by creating that VI matrix. That's a function of G and R. If you have no random effects, it's a function of just R. And we're going to walk through that on the next slide, which is going to be, I promise, the last slide that I will talk about today. So, VI, your variance-covariance matrix that helps you handle the correlation in your data, is equal to ZI, which is a matrix of your random factors, times G times ZI prime plus RI. So you see that VI will end up being subject specific, and it's equal to ZG prime plus R. So in proc mixed, you don't specify the variance-covariance structure of the observations directly, even though that's what you're interested in. Okay? You define it by giving two inputs to create that VI. One input that you provide is the R matrix for the residuals, and another one that you provide is any random effects. You do not have to provide random effects. You do not have to specify an R matrix. Either one or both of them together will generate a non-independent variance-covariance matrix for your results. But the structure of that matrix will vary depending on your choices of R and G. Okay? And these expectations and variances, these are gotten very similar to what we did on slide 44, but somewhat more complicated because you have to do, matrix math. So I will definitely not be walking you through that because I probably couldn't do it. In fact, I'm sure I couldn't do it. But trust me, it works out for a linear model to V equals ZGZ prime plus R. And again, I really want to emphasize this because I had trouble getting this before late in the course. So if you've zoned out, come back to me for like 15 seconds. I want to repeat this, and I really want you to grab this one. It's okay, I zone out all the time. But if you're playing a game or reading an email, come back to me for 15 seconds. The way that we account for correlation is by creating a variance-covariance matrix and or a correlation matrix there. You can go from one to the other pretty easily for your responses. That's what you're concerned about, modeling the correlation in the responses in your data. That is the VI matrix and the CI matrix. That's your ultimate goal. Anything else that you specify is just inputs to get there. So R and G are inputs to get to V, as shown by this equation. So, if we have a single random effect, then the G matrix is just a 1-by-1 matrix with the variance of the random intercept, which we said earlier was sigma naught squared. Z, it turns out, is a column matrix of 1s, and so Z prime will be a row matrix of 1s. So we end up with ZGZ prime equals sigma 0 squared times a 6-by-6 matrix if we have 6 observations per subject, okay? Times a 6-by-6 matrix of 1s plus the R matrix, which we defined as sigma squared I6. What is I? I is the identity matrix, or the independence matrix. So what it means here, remember when we said that the BIs and the EIs were mutually independent? So we're assuming that there's no more correlation in the data after we've accounted for the one random effect. We're going to let that do it. We're not going to bother specifying an R matrix because we're cool with the residuals being independent after we take into account the random intercept, okay? So that's why the identity matrix down here. So once you work out the matrix math, and you should have the tools to do this on your own at this point, you can see, and I think you may actually have to do it for your homework. Maybe that's the extra credit question. I don't know. But it's fun. It's good. It's good practice, really. Once you work out ZGZ prime plus R, you will see that V has that compound symmetric structure that we talked about because we've got a G matrix that's just a single random intercept and an R matrix that is independent. In proc mixed, you wouldn't even have to specify that. You could just say, here's one random effect, don't worry about the R matrix. Or you could say explicitly that the R matrix is independent. It's up to you. It'll give you the same thing. Because you're just saying that you don't have to account for additional correlation. So, this is not the only way that you can get a compound symmetric variance-covariance matrix for your responses. You could also get it by having no random effect and a compound symmetric R matrix. So, if we had no random effect, what would our G matrix be? It'd be blank, it'd be 0, it'd be nothing. So this whole ZGZ prime term would go away if we have no random effects. And what do we call that model? A model with no random effects. Linear model with no random effects. It is a Marginal linear model. Okay, so if we've got a marginal linear model, then V is just going to be equal to R, because ZGZ prime goes away. It's irrelevant. There's no random effects. So in that case, whatever structure that we specify for the correlation in the residuals is going to be what we end up with for our variance-covariance matrix for our responses. Okay? So two different ways that you can get the same ultimate structure and account for correlations in the exact same way. You could specify a compound symmetric R matrix, or you could specify a single random effect and no R matrix, or an independence R matrix. That's just a curious little quirk that I think helps you understand where some of these are coming from and where everything plays in. So if I'm not mistaken, that is pretty much as far as Dr. K got in the lecture that he posted online for you. I want to point out one last thing, which is, even if you were at my lab session yesterday, afterwards I thought, I was using some terms that maybe didn't really make that much sense, so I added one more slide. I made some slight tweaks to some other slides, but I added one more slide that you might want to go take a look at. I uploaded it about 1:30 yesterday, so if you downloaded the slides before, just go down and download them again if you want. But this is a summary of all of the different matrices that we're going to encounter in this course. Some of these things won't make sense to you, but I hope it'll be a useful reference guide as we go through and you say, wait, what is CI again? What does that mean? What does that represent? So NI is the number of observations per subject or cluster in your data. That's standard Dr. K terminology throughout the course. CI is an NI by NI matrix of the correlations between responses or outcomes for the ith subject or cluster. Here's a key point. CI is often simplified to C, because if we tried to estimate correlation parameters for every subject, we would quickly run out of data to estimate our parameters. Again, it's a simplification thing. So we often say that we'll just take the same correlation for every subject, rather than saying we want a different correlation matrix for each of our subjects or each of our clusters. VI is the only difference between VI and CI is it's a matrix of covariances between the responses and the outcomes, and it's often simplified to V. R matrix is also an NI by NI matrix of covariances, but it's the covariances between the residuals or the errors for the ith subject or cluster. And it's often simplified to just R. And then the G matrix is a little bit different. This is an M by M matrix of the covariances between your M random effects. So if you have one random effect, it's a 1 by 1 matrix. If you have two random effects, it's 2 by 2 matrix. If you have three random effects, it's a 3 by 3 matrix, and so on and so forth. So it gets bigger and bigger and bigger and bigger because you need to account for the variance of each random effect and the covariances between each of the random effects. And then I lied. One last thing, it's going to take 30 seconds, I swear. Okay. Correlation matrices have on their diagonals ones and on their off diagonals correlations. Covariance matrix, which can also be called a variance covariance matrix. It depends. I'll take either one. Sometimes it's easier to use the whole term a variance covariance matrix because then it makes sense why it's called VI, and it helps to differ from correlation. So here the diagonals will have the variances of your row and column variables, and the diagonals will have covariances. So variance covariance has just that. Variances on the diagonals and covariances. Correlation, ones on the diagonals, correlations on the off diagonals. That's it. I'm done. So I'm going to